So today I will prove the Hölder and the Minkowski inequalities. So let's fix p between 1 and plus infinity, and let me define by this symbol the integral of f to the power p, the absolute value of f of x to the power p, mu dx, and this at the power 1 over p. So if p is equal to 1, this is just the integral of the absolute value of f. And my claim, so the theorem, which will be Hölder inequality, so let me rewrite it. Which reads as follow. So let's assume that p is between 1 and infinity, and let me represent by q the value for which 1 over p plus 1 over q it's equal to 1. So I will call q the conjugate of p. And let's say that I'm taking here p between 1 and infinity, and when p is equal to 1, well, if p is equal to 1, this is 1, and therefore I will take q equal to plus infinity. So I'm calling q the conjugate of p. And what I claim is that if you take a function f such that the integral, so this, we will prove at the end of this lecture that this is a norm, that the p norm of f is finite, and let's assume that the q norm of g is finite. So I'm taking two functions f and g defined on some space omega, which satisfy this inequality. Then what I claim is that the integral of f times g d mu is finite, and actually it's bounded by the p norm of f times the g norm of q, the q norm of g, I'm sorry. So this is what's called Hölder inequality, and this is the theorem I want to prove now. So it's in the case in which p is equal to 1 and q is equal to plus infinity, so this norm g infinity is just the essential supremum of g. So remember that 2 lectures ago we defined the essential supremum. I will represent the essential supremum by this symbol, g infinity. And so what I claim is that, well, what this means in the case in which p is equal to 1 and q is equal to plus infinity is that, well, if the integral of the absolute value of f is finite, and if the essential supremum of g is finite, then the integral of fg it's bounded by the integral of the absolute value of f times the essential supremum of g. So this is our goal, and in order to prove this theorem, I will first consider the convex conjugated of convex functions. So this is what I will explain now. So let's assume that we have in R plus a function, let me call it f. so defined in R plus and taking values in R plus. And well, let's assume that f it's a convex function. And one example of a convex function will be the function f of x equal to x to the power p divided by p, where p it's a number larger than 1. So it's clear that this is a function which is convex. And what I want to prove that the following holds, that if I take x and y positive, then x, y, it's smaller or equal than x to the power p divided by p plus y to the power q divided by q, provided p and q are conjugate. So remember, I'm assuming here that 1 over p plus 1 over q is equal to 1, and I will be assuming now that p is between 1 and infinity with strict inequalities. So I want to prove this inequality, and because the proof of Hölder inequality is based on this inequality. But to prove that inequality, I will introduce what we will call the Legendre transform of a convex function. So let me go back here. If I have a convex function f defined on R plus and taking values on R plus, I will define the Legendre transform of f. Maybe I will represent that by t of f, whose value at theta it's equal to the supremum over all x positive of theta x minus fx. And what I claim I will not prove is that, well, if f it's a convex function, then t of f it's a convex function. What I want here to restrict my my goal to the case in which f of x it's the function xp divided by p, and define the transform of f by this formula and show that the Legendre transform of the function xp divided by p is the function x to the power q divided by q. So, and this is an elementary computation. Okay, so my claim is that if now I replace f of x by x to the power p divided by p, my claim is that this is equal to theta to the power q divided by q. So this is what I want to prove, and well, this is a very simple computation which I will present now. So first observe that if I take this function here, and let me call that function maybe g of x, which theta here is fixed, right? It's a positive number, it's fixed, so maybe let me call g theta of x. That g theta at 0, well, when x is equal to 0, g theta of 0 is 0, and its derivative at 0, well, I take the derivative at 0 of this function as a function of s. Since p is strictly larger than 1, the derivative of this expression is 0, this one is theta, so this is equal to theta, and this is strictly positive. So the function g theta, let me describe the graph of this function. At 0 it's 0, its derivative at 0 it's theta, and theta is strictly positive, so it goes here. It starts like that. Then my second observation is that if I take g theta of x and I send x to plus infinity, then you see there is a first piece which is linear, well, but this one it's superlinear, so the limit as x goes to infinity of this expression, it's minus infinity. So my function at plus infinity, g theta goes to minus infinity. So you see that if I want to compute the supremum, well, I have to care about the critical points of this function. So let's investigate what are the critical points of the function g theta. Let me consider the equation g theta of x equal to 0. So when I take the derivative in x, what I get is that theta should be equal, so taking the derivative of this expression, I have p which will cancel to p, and then x to the power p minus 1. So there is only one critical value which takes place at x equal to theta to the power 1 over p minus 1. And this is, well, since the function is increasing at 0 and goes to minus infinity at plus infinity, this is a supremum. So this supremum, the supremum in x of theta x minus xp to the power divided by p, well, I just have to replace x by t to the power 1 divided by p minus 1. So this is t to the power 1 plus 1 over p minus 1 minus 1 over p. X, it's t, so this is theta at the power p divided by p minus 1. And this is equal to, well, here I have p divided by p minus 1, here also. So I have 1 minus 1 over p. But mind that 1 minus 1 over p, it's 1 over q. So I get 1 over q. And here the power theta at power p divided by p minus 1. So let's see what's p divided by p minus 1. So if here I multiply by everything by p, what I get is that 1 plus, maybe let me multiply that by pq. So I get here q plus p, which is equal to pq. And so q, it's equal to pq minus 1, and therefore p, it's equal to q minus 1. Well, and by symmetry, what I get is that q, it's also equal to p divided by p minus 1. So what we have here, it's exactly p divided by p minus 1, which is q. So this is 1 over q theta to the power q. So this is exactly what I wanted to prove, that the supremum in x, it's equal to theta to the power q divided by q, which is also, well, saying that the Legendre transform of the function x to the power p divided by p, it's the function theta to the power q divided by q. So this is what I wanted to prove, so I will erase everything and just keep this formula, which is what we need. And this formula, it's very nice because, well, since this is a supremum, this expression, so let me write theta q divided by q, which is the supremum over x positive of theta x minus x to the power p divided by p. Well, since this is a supremum, this is larger or equal than theta x minus xp divided by p, and this holds for any x and theta positive. Well, since it holds for any x and theta positive, what I get is that theta x it's less than or equal to theta to the power q divided by q plus xp divided by p, which is exactly what I wanted to prove. So this completes the proof of this inequality. And, well, if you want, this is a particular case of a much more general inequality, which tells you that theta x it's less or equal than fx plus tf of theta, provided tf it's the Legendre transform of the function f defined by this formula. And let me write Legendre, which is the name of a French mathematician. So we proved, well, the same argument provides you that inequality if f it's a convex function and if t of f it's the Legendre transform of the function f. So now let's go to the proof of the Hölder inequality. Let me just remind that we proved that if x and y are positive, then x, y, it's bounded by x to the power p divided by p plus u, y to the power q divided by q. And so we want to estimate f g d mu. So f g d mu by, if I take f as x and g as y, well, this is bounded by f to the power p divided by p d mu by linearity of the integral plus g q divided by q d mu. And therefore, we immediately get that this integral is finite provided these two are finite. So this was the first statement of Hölder inequality, is that if this integral is finite and that one is finite, then we get that this integral is finite. Well, this is not exactly the inequality we are looking for, but we can derive the one we are looking for from this inequality. And what I will do, it's a very simple trick. Well, I will introduce a, which is a positive number, and here in this left-hand side, I will multiply and divide this expression by a. So I will take f and I will divide f by a, and I will multiply g by a. So I didn't change the left-hand side, but then now I will apply that inequality not to f and g, but to f divided by a and to g multiplied by a. So here I will get a to the power p, because I'm dividing f by a, and on the second term I will get a to the power q. And observe that, well, this inequality, now I can just erase here a and 1 over a. So now the left-hand side does not depend on a. The right-hand side depends on a, and this inequality holds for all a. So I can just optimize that over all a. And if I call, so let me give a name, alpha, to the integral of f p d mu, and if I call the integral of g q d mu, if I call that beta, what I have to estimate is the infimum over all a positive of alpha, which is the integral of fp d mu, 1 over p ap plus, so this integral is beta, so what I have here it's beta aq divided by q. And I have to find, well, what is the infimum of this expression when I consider this infimum over all positive a. So that's another very simple computation. To, well, again, if you send a to plus infinity, this expression, which is positive, will converge to infinity due to a to the power q. And if I send a to 0, this expression tends to infinity due to this expression, this term here. So if I want to compute the infimum, I have to find the critical points in a of this function. So let's do that. So when I take the derivative with respect to a here, so this is a to the power minus p, so I'll get p which will cancel to this 1 over p, and I will get a minus p minus 1 or minus p plus 1. So this is the derivative of the first term, so let's go to the second one. So I get a q which will cancel to this q, and then plus beta a q minus 1. And so this has to be equal to 0, or in the same way, I can just look for a which solves this equation, and what I get is that, well, you see that I have here minus 1 and minus 1 there, so they disappear, and what remain is that alpha divided by beta, alpha divided by beta has to be a to the power q plus p. So this means that a it's equal to alpha divided by beta to the power 1 divided by q plus p. So this is the optimal way, and in order to get the value of this expression, I simply replace a by this value. So let me do that here in this piece of blackboard. So I'll just replace a in this formula by this expression. So what I get is alpha p divided by p, and then, well, it's 1 over a, so this is beta divided by alpha to the power p divided by q plus p, plus beta divided by q, and a, which is this expression, to the power q. So a it's alpha divided by beta to the power q p plus q. So now what we get here, it's 1 over p alpha. So I have 1 minus this expression, so it's alpha q plus p, right? Because, well, I have alpha to the power 1 minus this expression, so I get q. then beta to this power, which is p q plus p, plus 1 over q beta, but beta it's at power p, q p plus q, and alpha at power q p plus q. So you see what we get? It's exactly the same expression. Here we have beta to the power p divided by q plus p. Here also alpha to the power q divided by q plus p, as it here. So we can put these factors in evidence, and we get 1 over p plus 1 over q, but that's 1. So this is equal to alpha q plus p times beta p q plus p. So we just computed this infimum in terms of alpha and beta, which are respectively these two intervals. So I'll just report this computation here. So let me erase these two lines. And well, now I computed this infimum in A. I obtained that expression where alpha is this one and beta is that one. So what I get is that this is equal to alpha, but alpha it's the integral of f to the power p d mu at the power q p plus q times the integral of, well, beta, it's g to the power q to the power p plus q. So to complete the proof, it remains to compute this expression. And well, to compute this expression, maybe I can divide it by, so I have here q p plus q. So let me divide by pq and pq. So the numerator and the denominator will be divided by pq. So when I divide the numerator by pq, I get 1 over p. And when I divided the denominator, for the first term, I get 1 over q. For the second term, I get 1 over p. But 1 over q plus 1 over p, it's 1. So this is equal to 1 over p. So here, this expression, it's equal to 1 over p. And, well, by symmetry, this expression, you see that I get the same expression by replacing q by p. By symmetry, this expression, it's 1 over q. And therefore, we proved that this integral of fg d mu, it's less than or equal to the integral of f to the power p d mu, and this integral to the power 1 over p. And here, this integral of g to the power q, and the integral it's taken at the power 1 over q, which is precisely Hölder's inequality. So this completes the proof of Hölder's inequality in the case in which p it's assumed to be between 1 and plus infinity. So now it remains to prove Hölder inequality in the case in which p is equal to 1. So let me write what we want to prove. We want to prove that the integral of fg d mu, it's bounded by f1 times g infinity, where here, remember that this is the essential supremum of g. And here, well, just remember that this is the integral of f, the absolute value of f d mu. All right, so let me call the essential supremum of g Let me call that C. And recall that we proved that the measure of the points x such that g of x is larger than C, that this set has measure 0. Okay. So we want to estimate the integral of f g d mu. I will use linearity to rewrite this integral as the integral over the set of points x such that gx is larger than C of f g d mu plus the integral over the points x for which gx is less than or equal to C. This is just the linearity of the integral. Now, since this set has measure 0, we conclude that the first integral it's equal to 0. Right? Since this set has measure 0, this integral it's equal to 0. So the right-hand side it's in fact equal to this integral. But on this side, what we have is that we are integrating over all points x such that the absolute value of g of x is bounded by C. So here I can rewrite f g of x as fx times g of x. And I know that g of x is bounded by C, so I can estimate this integral by C times fx on this set. Now, by linearity, I can take this constant C out of the integral, and since this expression is positive, I can estimate this integral by the same integral without intersecting the integral with this set. So this is bounded by C times the integral of the absolute value of x d mu. And this is exactly what's written here, right? C, remember, is the essential supremum of g, which is there, and the integral of f, it's exactly what we are representing by this object. So this completes the proof of Hölder's inequality in the case in which p is equal to 1, and well, this is Hölder's theorem. So now let me state Minkovski inequality. So let me take two functions f and g such that the p norm of f is finite and the g norm of f is finite. But the definition it's still on the blackboard. And what I claim is that if I take, well, that the triangle inequality holds. So if I take the p norm of f plus g, then this is bounded by the sum of the p norm of f with the p norm of g. So this is a triangle inequality which I want to prove for any p between 1 and infinity, and observe that for p equal to 1 this is elementary because the L1 norm, the 1 norm of f plus g is just the integral of f, the absolute value of f plus g. The absolute value of f plus g it's less than or equal to the absolute value of f plus the absolute value of g, which is what's written on the right-hand side. So this theorem, it's elementary for p equal to 1, and we will prove it for p between 1 and plus infinity. So let's prove the theorem, and for that we will so remember, I'm assuming that f p is finite and g p is finite. Otherwise, the inequality is trivial. So if you go back to the statement of the theorem, if you assume that one of these two is plus infinity, then the inequality is trivially correct. So let's assume that these two are finite, and I want to estimate this expression. And remember that here I'm assuming that p is larger than 1 and it's finite. So we will write this expression as, well, f plus g to the power p minus 1, f plus g d mu. And, well, here it's clear that this expression, it's less or equal than f plus g, and therefore I have two integrals. The first one is the integral of this expression times that one, and the second one, the integral of this expression times g. And we will use Hölder inequality in order to estimate this the first integral, which is f plus g to the power p minus 1 times f. So I want to use, at this point, Hölder inequality in order to estimate that. Well, this expression, by Hölder inequality, it's bounded by the integral of f plus g to the power. So I will use q for the first one and f for the second one. So I'll take the power q here, d mu, 1 over q, and then the integral of f p d mu 1 over p. Right? So I'm just using Hölder inequality. I'm taking q as the conjugate of p, and I'm using Hölder inequality by using the power p for f and the power q for f plus g to the power p minus 1. Well, we do exactly the same thing for the second integral. So for the second integral, what we have is that this expression. We apply Hölder inequality, which tells, well, we have the same expression here. The first term will be the same one, and the second term will be exactly equal to that one if we replace f by g. But if you recall, this is just what we represented by the norm of the p norm of g. So up to now, what we proved is that this integral, it's bounded by this one times the p norm of f plus this one, which is the same, times the p norm of g, and this is what I'm going to write here on this line. That what we proved is that this expression, it's bounded by right, so this is exactly what we prove up to now. I rewrote here the expression which appears there, and these two are just the p norm of f plus the p norm of g. So we arrived at that line, so now I will release these two lines to compute what p minus 1 times q is, and to complete the proof of Minkovski theorem. So p and q are conjugate. This means that 1 over p plus 1 over q, it's equal to 1. So let's multiply this expression by p times q. In the first one, what we get is q. In the second one, we get p, and this is p times q. So what we have there, it's p times q minus q, and you see that p times q minus q, it's equal to p. So this expression, which is appearing here, it's just p. So let me rewrite that as f plus g to the power p d mu to the power 1 over q f p plus g p. Now, on the left-hand side, I have exactly this expression to the power 1. So what I want to do is to divide it. I just have to be careful to divide because, well, maybe this expression is equal to 0. So if this expression is equal to 0, well, which may happen, for instance, if g is equal to minus f, well, but then if this expression is equal to 0, Minkovski inequality is trivial. So I can assume that this expression is different from 0, and in which case I can divide the left-hand side and the right-hand side by this expression to get that the integral of f plus g to the power p d mu, and when I divide the left-hand side by this expression, what I get is here power 1 minus 1 over q, and this is exactly 1 over p because p and q are conjugate, which is when I divided the right-hand side by this expression, the right-hand side becomes fp plus gp. Right? And so since this is 1 over p, this is equal to f plus g p, and we get here exactly a Minkovski inequality, so this completes the proof of the theorem. So let me go back to the statement of Minkovski theorem. So we proved that for p from 1 to, if p is greater or equal to 1 and finite, we have Minkovski inequality. Well, we already proved, so remember that I'm representing by this symbol the essential supremum of a function f. And we proved that inequality in the first lecture of this chapter in the case of essentially supremums. So in fact, this inequality holds also if p is equal to plus infinity, and therefore we have the Minkovski inequality for all p between 1 and plus infinity. So this is a first remark. And now I will, for p between 1 and plus infinity, I will represent by LP. Maybe if I want to say that the integral is taken with respect to mu, I'll say LP of mu. The set of all functions f from omega to r bar, which are f measurable, such that the integral of fp d mu is finite. Okay. So let me represent this set by this symbol, LP of mu. And what I claim is that this space is linear, which means that if I take f in LP and another function g in LP, and if I take a number a in R, what I claim is that AF plus G also belongs to LP for any P, remember, P between 1 and plus infinity. We have seen that this statement holds if I take P equal to plus infinity, so I can concentrate it here in the case in which P goes from 1 up to infinity. Well, for that, I first claim that AF belongs to LP. For that, we just need to go back to the definition of this integral. So take a function f which is in LP. This means that this integral is finite. Now if I take AF, well, AF to the power p, it's a to the power p, f to the power p. By linearity, I can remove AP from the integral. This is finite, AP is finite, so everything is finite, which means that AF belongs to LP. So in order to prove this statement, what we really need to show is that if I take two functions, g and f in LP, then f plus g belongs to LP. And this follows from Minkovski Inequality. Well, if f and g belongs to LP, this means that these two numbers are finite by definition of LP, and therefore by Minkovski Inequality, the integral of f plus g to the power p, it's also finite, which means that f plus g belongs to LP, proving that LP is a linear space. So to complete this section, I just want to show that Fp, it's a norm. A norm in the following sense. So if I take a number a in R and f in LP, then AFP is just A times FP. And well, this is clear from the definition of FP. We proved that already if P is equal to plus infinity, so I will concentrate in the case in which P is strictly smaller than infinity. So if you go back to the definition, you have AF. So this becomes a to the power p times this expression. It can go out of the integral because it's a number, so it's AP. Now you can multiply, but AP to the power 1 over p becomes A. So this proves this fact, which is very simple. Now my second claim is that if f is equal to 0, then f is equal to 0 almost surely. So f belongs to the equivalence class of 0, and this is also clear since the absolute value is non-negative. If this integral is equal to 0, means that we have seen already in the properties of the integral, this means that f has to be equal to 0 almost surely. And then the third property we have to prove, it's the triangle inequality, which means that if I take f plus g, this is bounded by fp plus gp, and this is exactly Minkovski inequality, Minkovski theorem. So the triangle inequality holds, and therefore we have here all the properties of a norm. So this proves that this expression is indeed a norm. And this completes this section.